So yeah, I'm going to talk about a study that's got a lot of co-authors who've already, or certainly on the call today, and we've heard from certainly Kat and Jill and so on. So this is about looking at climate feedbacks, but particularly looking at the chemistry and aerosol feedbacks. So I was just going to go into a bit of a theory about what we mean by climate feedback, just in case people aren't that familiar. So climate feedback, which we call alpha, is how the top of atmosphere radiation budget responds to a change in surface temperature. And Jonathan Gregory had a famous paper out, which is this plot on the left that shows you get a decrease in the net radiation budget as temperature warms, and the slope of that decrease is called the climate feedback. And the climate sensitivity is proportional to 1 over this, or minus 1 over this feedback parameter. We can split this feedback into lots of different processes. People usually use think about this in terms of clouds and snow and water vapor and so on, but today we're going to use this same sort of formulation to break it down into the contributions from chemical species. So the alpha is proportional to, or is equal to 2 terms, basically the rate of efficiency of a species or a species change times how that species changes with temperature. And I've got some plots in next slide to illustrate exactly what that means. So it's not just a dry formula. And how we've done this is using, again, the CMIP setup that Jill has just talked about. So we're going to focus particularly on natural emissions, how naturally emitted species change with temperature. We can get the rate of efficiencies from these species just by doubling the emissions. So here's a table here of some of the emissions that we're going to double to look at their rate efficiency. So dust, sea salt, DMS, lightning NOx, and BVOCs. And then we can calculate the sensitivity terms to temperature by doing some change where we perturb the surface temperature in a model. And the simplest way of doing that is using abrupt 4 times CO2 experiments. So they give you a roughly sort of so they give you your surface temperature change, and that will tell you how much your emission or concentration has changed with temperature. And so here I'm illustrating these parameters, these phi and these gamma terms. So the left-hand column is the phi term. So in each of these, this is the change in radiative balance from doubling the emissions of one of these species, from dust, from sea salt, and from DMS. And then the right-hand column is how these species vary with climate. So this is the change in emission for a 4 times CO2 scenario, temperature change. For dust, the change in, if you change emissions of dust has a both warming and cooling effect, and it turns out there's very little net change in the rate of forcing when you perturb dust. Sea salt, in contrast, has a very strong negative effect. So if you increase sea salt emissions, you have very strong negative terms. You can see particularly over the southern oceans here. And it also has quite strong responses to climate change. So on this middle right-hand plot, you can see the big red values show where sea salt emissions are increasing with a warmer climate. Then the bottom one is looking at DMS. This doesn't have quite a strong rate of forcing as the dust, and has a similar-ish response to the sea salt, because in both cases these are predominantly driven by changes in the wind, although there is some temperature-based inhibition of DMS emissions in the tropical region, so it's not quite as red as the sea salt plot. So those were species that are just pure sort of aerosols. if we want to look at some species that affect both ozone, both aerosols and ozone, then it's slightly more tricky to pick them out because the standard ERF calculation basically combines everything. So one way is to use the GAN diagnostics that Jill just explained. So we can look here. So the top left plot is showing the direct radiative forcing due to direct aerosol forcing from doubling BVOC emissions, and you can see blue values over the main forested areas, so that's not surprising. So we've increased our SOA, just as Kat explained. And we can also look, as Jill explained, the cloud effect. So again, of those three regions, particularly Amazonia, Central Africa, and Indonesia, we've got large negative forcing because these BVOCs have affected clouds. Then if we come down to the lower left plot, basically we can say that any radiative forcing left is likely to be due to ozone. That's slight oversimplification there, but we don't have other diagnostics to pull that apart just yet, although we are looking into this. And you can see, particularly here over India, there seem to be large increases in radiative forcing due to, which we hypothesize is due to the ozone. I should say ozone radiative forcing is always largest over desert regions, so this sort of could possibly explain the pattern of this ozone forcing change as well. And then the last one, the bottom right, is showing how emissions change in this full-time CO2 climate, and we've got big increases in emission over these main forested areas, over the Amazon, Central Africa, and Southeast Asia.
Less than 1 minute, Bill.
To the last slide. So what we can do is then combine these. So on that very first slide, I had a sum, so we can sum up all these AI terms, each individual feedback, by multiplying these phi and gamma terms that we've just listed. And so that's what's in this bar chart here, showing the feedback term from each of these processes. And first thing to notice is that they're nearly all negative. So in most cases, we're dominated by changes in aerosols, and the feedbacks due to aerosols are pretty strong, much stronger than any changes in ozone. The only exception to that is the models actually show quite a large wetland change in wetland methane emissions. So that is a slight positive feedback, but overall it's looking like the effect of chemistry and aerosols on the climate feedback is negative, and we come up with a value here in the models of about -0.23 as a feedback factor. Now that it's a feedback parameter. That might not be too intuitive to people, so I've just listed here what other physical feedbacks are. So -0.23 is a similar order of magnitude to what we might expect from, for instance, the snow albedo feedback. So they're not as chemical feedbacks aren't as strong as the physical feedbacks, but they're not negligible compared to them. So that's it. Thank you.
Thank you very much, Bill. One question for you so far from Alex. Thanks for a really stimulating study, Bill. Are the changes or the maps that you've shown, are they the multi-model means, and what does the spread spatially look like?
Yes, they are multi-model means, and they're certainly different species have different spreads. The one with the most spread is the dust, because in some models actually the CO2 inhibits dust production. It makes the vegetation grow and reduces dust, whereas in other models they don't have that parameterization in there, and CO2 makes it more arid and more dust. So yeah, so whereas others, the sea salt, it's a bit more it's purely wind based, and most of the models agree on the amount of wind changes. So it depends which species you're talking about.
And a secondary question then, why is Wacom and GFDL so different for aerosols?
Right. I guess why are they so different? I mean, because they're just different models. I mean, we've seen talks this morning about how UKCA can be very different in cases. So I haven't explored specifically why each model is that different.
And another comment from Matt, is it possible to group the analysis by models ECS? I wonder if it might highlight some of the intermodal differences.
So the model ECS doesn't affect the calculation because we scale the change by the change in surface temperature. So when I was looking at the change in, let's say, the sea salt emissions, that's scaled by each model's change in surface temperature. So if it has a higher surface temperature change, that's factored out. But as to whether these processes contribute to models having higher or lower sensitivity, I guess that is indeed something we could look at. But as I show, the overall effect seems to be negative. So you would imagine in this case, the models with the most sensitive chemistry would give the lowest ECS, but I haven't tested whether that is really true.